All right, let's dive right into this explainer and tackle one of the most mind-bending questions out there. We're going to explore the absolute limits of our cosmos. We'll start with what we can physically see through our most powerful telescopes, and then journey way out into what mathematically must exist. It's that ultimate question that's been keeping humanity awake at night for centuries, right? Where does it all actually end? So just imagine for a second that you're in a spaceship. You point it in one random direction, hit the gas, and just keep going. Forever. What actually waits for you at the very end of reality? Do you eventually smash into some giant physical brick wall? Do you punch through into an endless dark void? Or do you somehow loop right back around to Earth? Or, and this is where it gets crazy, as some modern theoretical physicists suggest, do you hit a mathematical boundary where space and time literally dissolve into a holographic projection? Well, to figure that out, we need to build our understanding step by step.
Okay, let's ground ourselves in the actual science first. When astronomers talk about the universe, they're almost always talking about the observable universe. Basically, think of it as a massive spherical bubble, and we're right smack in the center. It represents the absolute limit of light that has actually had enough time to reach us since the Big Bang, which was roughly 13.8 billion years ago. And we're actively mapping this colossal visual bubble right now with incredible precision, using tools like the European Space Agency's Euclid telescope, which is out there building a massive 3D map of the cosmos across space and time.
Now, just look at this number, 93 billion. That is the diameter of our observable universe in light years. It's a scale that is honestly almost impossible for our human brains to truly wrap around. But wait a minute, you might be wondering. If the universe is only 13.8 billion years old and absolutely nothing can travel faster than the speed of light, how on earth can the bubble we see be 93 billion light years wide?
And that brings us to this completely mind-boggling fact. The observable universe is actually physically bigger than the age of the universe. How? Because the space between galaxies is expanding. And here's the real kicker. Empty space itself isn't restricted by that cosmic speed limit of light. Because space is continually stretching out, the edge of our observable bubble is actually receding away from us faster than light can travel. So distant galaxies are constantly vanishing beyond this invisible horizon, literally never to be seen again. Section 2. Beyond our visual bubble. Crossing the cosmic horizon. So if we cross that horizon, what exactly is lurking out there in the unobservable universe? The space way beyond the reach of light. Well, here are the main scientific suspects for what exists past that 93 billion light-year mark. First up, it could literally just be more of the same, stretching out infinitely. Second is the multiverse theory, where our universe is really just one inflating bubble among countless others. Third, we've got higher dimensional structures. Astronomers have actually observed this phenomenon called dark flow, where entire galaxy clusters seem to be pulled by immense, unobservable forces from outside our visual horizon. And finally, theoretical physicist Nikodym Poplavsky has put together a mathematical hypothesis that our entire universe might actually exist inside the event horizon of an unfathomably massive black hole belonging to a parent universe. Wild, right? But before we get completely lost down the multiverse rabbit hole, let's look at how edges actually work on a smaller, much more relatable scale, like right here in our own Milky Way galaxy. For the longest time, we actually didn't know where our galaxy ended. But recently, scientists figured out that the Milky Way's star-forming boundary stops at about 40,000 light-years from the center, yet we still find stars further out than that. Why? It's because of a process called radial migration. Basically, stars are born inside that boundary and then slowly drift outward over billions of years, kind of like cosmic hitchhikers. It's a great illustration of how edges in space are rarely, if ever, hard brick walls. They're usually just gradients that slowly fade out into the dark. Moving on to the shape of space, finite but unbounded.
To really grasp the ultimate shape of space, we have to separate two absolutely crucial concepts: geometry and topology. Now, geometry is the local curvature of space. Think of a little ant walking around on a piece of paper. To the ant, it feels perfectly flat. But topology, that's about global connectivity. What if you take that same flat piece of paper and tape the edges together to make a cylinder, or even a donut shape? The geometry is still flat as far as the ant is concerned, but the topology connects the whole thing together in some really bizarre ways. You know the classic arcade game Pac-Man? It actually perfectly illustrates a finite universe with absolutely no borders.
If you fly your little spaceship off the right side of the cosmic screen, you don't hit a wall, you just instantly reappear on the left side. It has a mathematically flat topology, but it's closed. This means you could theoretically have a universe that is incredibly large, completely finite, and yet there is absolutely no physical edge to fall off of.
Let's break down the possibilities based on the cosmic microwave background data, which is essentially the afterglow of the Big Bang. A flat universe has zero curvature. An open universe curves outward, kind of like a saddle. And a closed universe has positive curvature, sort of like a sphere. Now, our current observational data strongly suggests the universe is remarkably flat, at least within our little observable patch. But remember that ant on the paper? Just because it looks flat locally to us doesn't necessarily mean it isn't slightly curved on a massive global scale.
In fact, some recent cosmological papers, like one published by physicists Berwig and Assen, argue that a slightly closed universe actually solves some pretty massive problems in physics. It elegantly avoids the whole paradox of the Big Bang's singularity. Think about it. In a closed loop, the universe doesn't have to explode from a single point of infinite density. Instead, it could act as a continuous bounce, just eternally expanding and contracting without ever hitting some unexplainable mathematical wall. Next up, the holographic boundary. Dissolving space into information.
Okay, so this is where things get truly mind-bending. What if distance, space, geometry, and time aren't actually the fundamental physical realities of our universe at all? What if our cosmos is bounded not by physical space, but by a finite collection of information, about 10 to the power of 122 bits to be precise? In fundamental physics, an edge isn't necessarily a border you just bump into. It's the absolute limit where our everyday concepts of space and time completely break down and dissolve into pure quantum data. And that brings us to a literal game changer in modern physics, Juan Maldaceni's ADS/CFT correspondence. Back in 1997, Maldacena proved that, mathematically, gravity in a three-dimensional volume is exactly equivalent to a quantum field theory on a two-dimensional boundary. Or, as he puts it, the universe we live in, the bulk, emerges entirely from that boundary theory. There is literally no outside to fall into because the boundary is the very thing projecting the inside. Here's exactly how that mathematical duality works. Step 1. You have a two-dimensional flat boundary that is just filled with quantum information. Step 2. Quantum fields interact on this flat surface. Step 3. Those interactions mathematically project gravity and a third dimension outward. And finally, Step 4. The three-dimensional reality that you and I are experiencing right this very second emerges as a hologram. Three-dimensional reality is simply the emergent code running on a lower dimensional edge. The edge isn't a wall at all, guys. It's the source code. It's amazing to look at how rapidly this science is moving, too. In 1971, Stephen Hawking showed that black holes have horizons, edges that swallow everything. But physicists soon realized these horizons actually act like hard drives, storing 3D information right on a 2D surface. Then, by 1997, Maldacena proved this holographic duality applies to the cosmos itself. And today? Right now, we are literally using advanced quantum computers to simulate how three-dimensional space emerges from these 2D mathematical boundaries. It's happening as we speak. Finally, is there an outside? The meaning of everything. We've explored the physical edge, the geometric edge, and the informational edge. But to really answer what lies beyond absolutely everything, we have to strictly define the word universe. If the universe means the totality of existence, every single particle, every dimension, the rules of physics, and the very fabric of the vacuum itself, then an outside is a logical impossibility, because an outside observer would still be a thing, and a void is still a space. Because nothing is still a concept, an absolute edge separating everything from nothing just simply cannot exist. And honestly, this is where you come into the picture. As the pioneering string theorist Leonard Susskind points out, the observer is part of the boundary layer. In this holographic view of reality, human consciousness itself might actually be a node positioned right at this informational edge. We are literally the universe's mechanism for looking inward at its own depths and outward toward its own conceptual limits. We are part of the edge. Which leaves us staring right into the void with the ultimate question. We've learned that edges in space are really just gradients of stars, that flat reality might actually loop back on itself like Pac-Man, and that the universe itself might just be a hologram projected from a boundary of pure quantum information. But if the universe truly encompasses absolutely everything that can be measured, simulated, or experienced, what exactly is nothing? keep pondering that one. I really hope this explainer has completely changed how you look up at the night sky.